I'm a staff research scientist at Meta Generative AI department, and today we'll talk about computer vision research in 2023 until now. A brief overview. So, nothing spectacular happened in non-generative computer vision in 2023. This is, I just wanted to make it clear at the beginning so everybody knows. No high expectations, so to speak. If you look at the keywords of the papers at CVPR 2022 versus 2023, you would see a clear trend that diffusion models got hyped, and it's by almost 600 more mentions in the papers than the previous year. It's a huge boost in popularity. You can also see a small improvement, small increase in popularity over the nerves and radiance fields, which is about 3D reconstruction, and about the CLIP, which is contrastive language image pre-training. The rest, attention, CNNs, contrastive pre-training, transformers, and even VIT, which is a visual transformer, got less popularity the latest CVPR. So the most important thing in 2024 in computer vision is three aspects: scale, compute, and data. So you want to increase the model size, increase the compute available for your training, and improve the data and quality and size. What we will talk about? We will talk about visual representation learning mainly, which is about perception and not generation. We'll talk about scale of three components. We'll also mention a little bit about techniques, existing techniques for self-supervised pre-training, and novel techniques appeared this year. We'll briefly go over multimodal models and fine-grained tasks like segmentation and tracking. What we will not talk about today is about 3D. We will not talk about generative models because Alexander Nochenko, next speaker, will talk about generative models in details. We will also not talk about Jan LeCun's JEPA because it's a little bit different kind of models and too complicated for this brief overview. Let's start from architectures. The main fact here is that VIT, Vision Transformers, is still running the game. It's the best architecture out there. Nothing novel appeared this year. So with a small remark that there are a few improvements over VITs, like marginal things, technical things. For example, the first one is called Navit, which is a vision transformer for any aspect ratio and resolution. The main idea here is that before that, you would take, in the CNN era, you would take images, resize them to exactly the same resolution, all squares, for example, and you aggregate them in a fixed batch of size K, and you feed it through the model. This way, you'll have to retrain or fine-tune the model if you want to increase the resolution and improve the quality of the perception. In this paper, authors suggested that why not just aggregate a bunch of randomly sampled images with different resolutions, with different aspect ratio in the same batch, and just tokenize them, as you can see on this diagram. Tokenize every image of different size. You drop tokens randomly, which is a common technique in pre-training VITs. And then you just reshape them in a single sequence of tokens and throw it in the model. Training on arbitrary resolutions would allow you to get much better performance overall because the model sees more different variations of objects and their scales. At the same time, you can save compute based on the fact that the smaller images require less compute to be processed, and the larger images, they are more expensive, but you would not have very often like very large images in the batch because you sample them randomly. On the plot on the right, you can see that this technique allows you to improve pre-training time by 4 times. Basically, you save a lot of compute and achieve the same performance 4 times faster. And also during inference, you have flexibility. You can choose if you want a quick response, you just take a small image. If you want to get a very precise answer, you just feed it a large image, and it takes a little bit longer, but you'll get a more precise detection results or classification Now we'll talk about scale. Researchers recently have been really fascinated about the scaling laws of the models because we want to know how good the models would scale if we increase, for example, the number of parameters, or we increase available compute, or we increase the amount of data which we feed to the models. But we don't want to train, we want to anticipate what would be the performance of the model, given that, let's say, we want to increase the training data size, and we don't want to train the model until we know that it actually makes sense for us to collect more data. And scaling law allows us to kind of fit the curve and predict what will happen if we increase one of the aspects in the model. Usually models scale in a power law scenario. So if you increase the model size, for example, the error rate would drop linearly with in the log scale of the model size. And this is one of the formulas. You can also say that you have epsilon infinity, which is a fixed term which represents a reducible loss. Basically, the model would always have some error irrespective of how big it is and how powerful it is. The first paper which we want to talk is VIT 22 billion. Google took basic vision transformer and scaled it up to 22 billion parameters, which is a huge milestone for computer vision, but it's not that big of a model in terms of language models nowadays, which go more than 100 billion parameters and like hundreds of billion parameters. But for computer vision, this was one of the biggest models so far. And it's much more difficult to scale vision models because the batch size, the batch of the images takes much more memory than a batch of sentences. And that's the main limiting factor here. So what was done on the architectural side to scale it up? Apparently, researchers figured out that you need to employ a novel block called parallel attention NLP. In essence, here you have regular self-attention on the left, and in parallel you have MLP branch. So you have at the same time a regular transformer, and in parallel you have a multi-layer perceptron. So we're going back to the roots, but now we combine them. This way you can blow up the number of parameters and improve the performance when you scale the model. There are a few tweaks with the layer normalization as well, but this is more technical and less important. The main thing here is that you scale the model up, you train it a bit longer, and you get improved performance on different data sets. For example, on the top, you can see the performance on the fine-grained classification on Naturalist 2017 dataset. You get +2, +3% performance when you scale up from 2 billion or 4 billion parameter model to 22 billion. So this paper got like 5x scaling up. And in the bottom, you can see that the larger model with 22 billion parameters achieves much better performance on the ObjectNet dataset, which is the dataset much more challenging than ImageNet in nature. And you can see that the performance just goes up directly when you scale the model. At the same time, this kind of pre-training on the large model allows you to do zero-shot retrieval, zero-shot classification on the ImageNet, also with a very solid performance, much better than the smaller models. Next paper is EvaClip 18 billion. So authors, it's pretty also a recent paper in 2024 even. Authors took the regular clip from OpenAI and took that architecture and scaled it up to 18 billion parameters. So it's a bit less than 22 billion on the previous slide, but this work is not from Google, and it's trained on the public data, and it's publicly available, the checkpoints you can use. Compared to the previous slide where the model was trained on an internal proprietary dataset, which is, you don't know what's there, and the weights are not available. On the left, you can see that when you scale up the model from the smaller size to the 18 billion, you get a direct improvement in performance, which is also expected. At the same time, it's very nice to see that we are not really like saturated and you can scale up even more. But I guess the guys who trained these models, they didn't have enough compute or enough data to go further. Another interesting technique here about scaling is that now we're at the point where we don't want just blindly blow up the model in all the dimensions at the same time, but want to cleverly approach that based on the amount of compute we have. Let's say we have amount of compute X and it's fixed. We want to figure out what would be the best architecture in terms of shape of the layers and the depth and the width, so that we can squeeze out the most out of the compute you have at hands. And the guys from Google also, they took the VIT transformer and explored different dimensions or how to scale that model. They took widths, they took the number of layers, and also explored the width of the MLP blocks, so the size of the layers in the MLP blocks in every self-attention layer. They trained around 100 different experiments and they fitted the curves. And they figured that the important thing is that smaller models can train at the optimal architecture shape. So if you cleverly select the shape of the layers and also the depth of the layers, you can achieve much better results with the same compute than previously known larger models, much larger models. You can see on the plot here, for example, actually in the table is better. In the bottom, you have pretty large models of 2 billion parameters, which achieve approximately the same result as much smaller 400 million parameters SOVIT. Basically, 5 times smaller model achieves the same performance if you approach the scaling of the architecture in a clever way. So you need to scale the size of the VIT more slowly than allocated compute. For example, you get 10 times more compute. It doesn't mean that you have to scale your model by 10 times. You scale the model only by approximately 2.5 times in the terms of number of parameters. And the optimal scaling here is that first you scale the MLP dimensions, so increase the width of the MLP blocks in your VIT, and then you scale the depths, and after the depth is scaled, you scale the width. So it's not all at the same time, but it's a clever choice of what to scale and when. Now let's talk about better data and how to get the data and why it matters. So in this slide, we will talk about data filtering networks. This is a paper from Apple, which is a surprise. Usually Apple doesn't publish much and they don't really open source anything, but this is one of the exceptions, which is a very interesting paper where authors studied how can you approach the filtering of the data in a methodological, exhaustive way. Usually what you do when you want to train a large VIT, you take a large corpus of uncurated data from internet, let's say a common crawl data set with 12 billion uncurated images, and then you apply some filtering technique to filter out the best image and text pairs in terms of alignment, because most of the labels are noisy there. And the standard way is to take OpenAI's pre-trained clip and use the scores of the alignment of the image and the text to figure out which pairs are less reliable. You throw them away, you are left with like 10 times less data, and then you train. So that was the de facto standard technique in the public domain in the research. And Apple guys, they challenged that by studying what is the best model to use to filter the data. So not just taking OpenAI's clip, but they tried different other models and trained them on different data sets. So the main idea here is that when you want to prepare a curated data set with filtered data, you don't need to have very strong filtering model, but you can take a less strong model, but trained on very clean data. You take, let's say, 100 million image text pairs, but manually curated, annotated by humans. You train your filter network, then you apply that model to filter a larger corpus of images from internet and captions. And after that, you train your final model and you get this green line here, which is improved performance compared to the red line. Red line here is OpenClip, is a implementation of the OpenAI's clip on the public data, and you clearly see that the gap, the dots was the same shape, they represent the same model size, the same architecture, but you can see that the data actually is determining the performance of your model by a huge degree, which kind of we expect that, but this is a nice experiment showing that the quality of data really matters. Now we come to the interesting paper called What Does Clip Know About a Red Circle? It's about visual prompting. So we want to kind of control the model and tell the model where to look at. So authors did interesting experiment. They took a few images and they highlighted some specific objects or parts of the objects with red circles and queried the model to find the appropriate caption for the annotated image. And surprisingly, if you just take any image and draw a red circle around the object, the model would focus exactly on that part of the image, but at the same time, it would retain the general context of the image. For example, you have two sheep on the image and you draw a circle around a small lamp, and surprise, surprise, the best caption would be the white lamp, the white little lamp for this image, and not just two sheep in the wild. The same works for image parts. You select an eye or a nose or a mouth of the dog, and it will highlight that the best matching caption would be eye, nose, or mouth. So this is an interesting emerging capability of clip-like models or large visual language models, where the hypothesis is that why does it happen? Because probably there are some labeled images with red circles in the dataset. Authors checked how many of these images are there in the training dataset. Apparently, it's pretty rare. So there are only few image examples like this, but the models can capture even these rare occurrences in dataset. With one remark that only the larger models can do that. If you take a small model, like a few 100 million parameters, it will not be able to capture these low frequency scenarios. But if the model is large enough, it will be able to capture even these rare events, and it will also react on the any highlights on the images, especially the red circles. But this also brings us extra bias in the model. So basically, we re-emphasize the bias in the data through our models. You take any arbitrary photo of a human and you highlight it with a red circle, and the probability that the model says that it's a murderer or missing person improves drastically. For example, here you see the regular photo of a man and a woman, and the most likely class is a man or a woman. And then you draw a red circle around the man, and you get a murderer. Or you draw a red circle around the woman, and you get a missing person. Yeah, so we need to be careful with this kind of data, and that could introduce undesired biases in our models when we deploy them. And before this paper appeared, nobody even thought about that this can happen.
I'm sorry. Is this about this? This was in a data set.
Yeah, this is most likely because in the data set, red circled humans usually appear from the like newspapers or some police reports. Yes, it's like the most obvious use case, and that's why the model learned to the co-occurrence of the class label of murder or missing person with the highlight.
Right.
Yeah.
So if it was a green square, maybe the effect was different.
The with green actually, so they also checked different kind of labels, and the red circle is the most prominent. It works. The rest doesn't really work much. It can highlight something, but it's less of a problem. Let's talk briefly about self-supervised techniques, especially the novel ways of pre-training the models appeared in 2023. The first paper is about changing the clip objective to improve the the alignment between the images and text. So it's a very small modification which can bring us a very solid performance boost. On this pipeline, you can see this is the image from the original clip paper, how it works. So you have an image encoder which tokenizes the image and produces embeddings for every image. And here you can see a bunch of images produced, bunch of images projected in a bunch of embeddings. Then at the same time, you have a text encoder which takes sentences, bunch of sentences, also projects them in the Latin space. And then you want to compute all pairwise relationships, like similarities between the text and images, and apply some loss which would pull the positive pairs closer and the negative pairs far apart. The standard way is to use a contrastive loss with softmax normalization here on the top. You just compute probabilities based on the similarity between every pair, and you softmax normalize them and make the positive probabilities closer to 1 and negative closer to 0. So the authors from Google, they suggested a small modification of that loss. Instead of using softmax, they suggest to use pairwise sigmoid loss, where the argument of the sigmoid is multiplied by the class label. It's either -1 or +1. So the idea, like the intuition behind the loss stays the same. You want the positive pairs probability to become higher and the negative lower. But the mathematical way of representing that in the loss is different. Very small change in the code results in a huge performance boost and more robust training, which is very I think now you should use that technique as the de facto standard technique when you want to train unified embedding space for images and the text. Next method is about the captioning. Usually before that, people would say that contrastive pre-training in a clip manner, on the left here you can see, is much better than pre-training using the image captioning, which was popular early in the days, but then kind of forsaken for some time. And now it gets back to us. Researchers say that if you do it in a clever way, if you tune your parameters, you can get the same performance or even better on some benchmarks as a contrastive pre-training. The model looks very simple. You have encoder, decoder, transformer architecture. Vision encoder takes image as input, tokenizes it, produces some latent tokens, and the decoder takes these latent image tokens and decodes them in the caption. So it's a sort of a generative model in a way because it can generate arbitrary captions. It's not like you take a predefined sentences and want to match the image with a predefined sentence, like in the case of clip. And this kind of captioning pre-training is better than contrastive pre-training for, of course, image captioning tasks, which is obvious because you have more flexibility. You generate the sentence on the fly. It's better for OCR tasks. So you pre-train this and then fine-tune for character recognition. It gives you much better performance. Also, it's much better on question answering than the contrastive pre-training. And for the classification, they achieve approximately same performance. Another way of pre-training large vision models is masked Out Encoding. This is technique based on the fact that when you encode your image in the tokens, in the visual tokens, you have a bunch of them. You can drop, let's say, 2/3 of the tokens and keep only 25% and ask the model to reconstruct the rest. So you look at the one quarter of the image and you want to reconstruct the rest of the tokens in that image. This doesn't require any labels, and it scales very nice with the size of the data and scales with the size of the model. And researchers from Meta showed here that you can use this MAE pre-training as a pre-training step. Let's say you have a weekly labeled dataset of Instagram images with some hashtags. Hashtags usually very noisy, and you use those noisy hashtags as a sort of class label, but very weak class label. And if you use only this kind of information, you get the blue performance here. So this shows the performance on different downstream tasks when you fine-tune or you linear probe the model after you pre-train it. So if you just use the WSP, which is a weekly supervised pre-training with this Instagram hashtags, you get this middle performance, which is not very nice. If you just use MAE performance pre-training, sorry, you get the purple performance, which is sometimes a bit better, but sometimes a bit worse than just weekly supervised pre-training. But if you combine them, first you don't use any labels, pre-train to reconstruct the tokens, and then you fine-tune it with weekly supervised training, you get the best performance. And you can also model parameters you can see on the plots. The more parameters, the better. Also, you can scale it with the size of the data set. And this kind of pre-training achieves state-of-the-art results on many benchmarks as well, which is pretty nice. This is another self-supervised pre-training technique called Dino V2. Appeared in 2023, but at the same time, this is an improvement over the previous Dino V1 version. Both are from Meta. And this is the technique which also doesn't require any captions. And it shows very strong generalization to out-of-domain data. Basically, you can pre-train this on a large corpus of uncorrelated or a little bit correlated data and apply that model to a bunch of downstream tasks. It will generalize very well. It's a de facto now a very strong encoder, which you can download the weights from GitHub and use it in any of the downstream tasks. It will generalize pretty well because it's not biased to any labels. It works in the following way. You have a VIT model, which consists of two models in a way. You have a student model, and then you have a teacher model, which follows the student weights, but in exponential moving average way. So it kind of a smooth out version of the student weights. Then you take an image, any image from the data set, you transform it, apply some augmentations like rotation, color augmentations, or etc. And you want the student encode the original image in the same way, like to get the same representation as the teacher would encode the transformed image. So you compare the representations and you get your loss and you propagate the gradients through the student, update the weights. In this paper, authors applied different tricks to improve the performance compared to the V1 version. I wouldn't go into details, but you can see that like a very long list of tricks. Every next trick improves the performance even further. Another contribution is that they showed if you take uncurated data, it's quite important to apply some automatic curation on it. For example, deduplication. If you have a large data set, you want to run some pre-trained encoder to find the very similar images and aggregate them like in the clusters. And then you use these clusters as augmentations of a single image instead of just a geometrical transformation. And that also gives a huge improvement. And here you can see the visualizations of the features trained by Dino V2 method. You can see that it fairly well understands the object parts and segments objects from the background. Now we come to multimodal part of the talk. In essence, the slogan of this part is let's glue everything with transformers. We can glue vision, we can glue text, we can glue other modalities, just unify them and feed through a large transformer. The first paper is image bind. It learns a joint embedding across 6 different modalities, not only images and text, but audio, depth, thermal, and IMU sensor data. In a nutshell, you just want to train in similar way as a clip, where you have only text and image. But here you have much more modalities, so you sample pairs of modalities. For some data, you have only IMU and heat map. For some data, you have only text and audio. For some data, you have other pairs of modalities like annotated in the dataset. So you just feed it through like a single encoder, and you want the representations of the same object, but in different modalities to have similar features. And you get the final embedding space, which kind of jointly learns about all the modalities. This allows us to have such cool applications like cross-modal retrieval. You get an audio and you want to retrieve all the similar images or all the similar videos which correspond to this audio in the dataset. Or, for example, you can also do arithmetics on the data. You take an image of a bird, this on the far right, and you take an audio of motor revving, you sum them up, the two embeddings, and you retrieve in the dataset from the videos, you'll get a video of a person going on the scooter through the stalk of birds, because it's a combination of the two objects which you used for arithmetics. Surprisingly, it's not very common in computer vision that when you train a generalist model on different domains, that generalist model would outperform every individual model trained on specific data. But this is the case here. The model trained on 6 modalities outperforms individual models trained on only one modality in specifics. And you can see on the bottom here, the plot showing, for example, if you take the audio model trained only on audio data, it's in gray, yet like significantly worse performance than if you train all the modalities at the same time, because you kind of pull the useful information from different models, and they help each other to boost up the performance of individual modalities. Now let's talk about how can we really make the models reason about images and answer questions in natural language. And this is a really interesting approach, at the same time very easy. So researchers from Microsoft suggested to do the following. You take a pre-training vision model, like one of the models which I described on the previous slides, and you take an image and you tokenize an image using that model, producing the latent visual tokens. And second, you take a pre-trained language model. It could be anything, could be Vicuna, could be Llama, could be Mistral. And these models, vision model and the language model, trained independently. One is trained on images only, another one trained on the text only. You combine them in a single model. So you extract the visual tokens from image, you extract tokens from the text, you combine it in a single sequence and feed it through the language model. And you ask that model to generate answer for you. Let's say I want to know what's on the image, or I want to count objects on the image, for example. And I fine-tuned these models all together on the new dataset of visual question answering. A surprise, surprise, this works pretty well. You can see on the diagram plot on the right. It's just striking that such a simple technique where you just combine two models in the same problem, and it works pretty well. And people also speculate that ChatGPT 4v actually employs something like this. It's separately trained vision and text, and then combined and fine-tuned all together on a large corpus of data. Of course, we would never know all the engineering tricks which OpenAI employs, because they never disclose that. But you can check the results. You can just open the chat. You send an image of some letter with cryptic handwriting, and ask the model to read for you what's written there, and it will answer, or just answer any questions based on the image you upload. This is another model following the same idea. It's from Google. It's exactly the same intuition, but they use slightly different text encoder and slightly different vision encoder. In the same way, they just tokenize an image, they tokenize the text, they concatenate the visual plus text tokens and feed it through some language model, you get an output. They just showed in this paper that you can do it much faster because you can like tune the size of the models accordingly. And the last part of the talk is about about segmentation and tracking. The first model is called SEM, segment anything. This model got a lot of hype in summer last year because it's the first foundation model for image segmentation, which can work on arbitrary objects, arbitrary images. Basically, you take arbitrary image, you feed it to the model, and you can also query that model with text. So it doesn't produce you a predefined set of labels like a sky, a car, a tram, but it would react on any prompt you like. For example, I want the model to segment a specific like head of the tram driver. I just ask, give me the head of the tram driver. It will give me a small mask of the head of that guy driving a tram, meaning that it's not limited to a predefined set of class labels. This is achieved by a pretty large VAT encoder transformer trained along with segmentation masks and captions. So the guys collected a pretty large data set of segmentation masks and text annotations, and that allows to scale up this and create a foundation model which we can use in any downstream application when we don't know exactly what kind of objects we want to segment at the end. Of course, it's a bit worse if then the model's trained on specific classes. Let's say I want to segment only cars and people on the street. For me, it's better to take the model specifically trained only on those classes. But this model can give you a very solid baseline if you don't have your data set, if you don't know in advance what kind of objects you want to segment. And how it works, you can see on the image on the right, animation. So you take an image, you extract the image features, then you get the latent tokens of that image. At the same time, you have a decoder which takes the latent tokens plus the encoded prompt. Prompt can be a text, it can be a point. You just click a point and it segments an object, or it can be a mask, partial mask of the object, which will generalize in like a full mask of an object. And the last paper which we want to talk today is a code tracker. It's better tracking of dense objects on the video, also using the VAT-like architecture. But here we combine CNN features with transformer. So we extract some pre-trained features using some CNN, and then we feed those features to a transformer to be able to track densely points on the videos. This model can track up to 70,000 points jointly and simultaneously. And here you can see very nice visualizations like a horse jumping or a guy doing paragliding. And it follows the densely every point of the object, which was not really possible before. And on the bottom, you can see comparison of the code tracker model with the state of the art, like the previous state of the art. You can see that most of the models fail miserably if the actions is too complex and rapid, but the code tracker is able to track the legs of the guy doing salto. So it's pretty nice.